reflection and refraction. We all know that light is a form of energy. We learned that light travels in a straight line. Light traveling as straight rays explains the phenomenon like reflection and refraction. But it fails to explain the phenomenon like diffraction of light. To explain this, many theories have been put forward by different scientists. Let us know about the different theories of light. The corpuscular theory. The corpuscular theory of light proposes that light consists of tiny particles called corpuscles. These particles travel in straight lines and bounces off surfaces, explaining reflection. This theory was originally proposed by Sir Isaac Newton. The wave theory of light. It suggests that light behaves as a wave, spreading out and interfering with itself. This theory explains phenomena such as diffraction and interference. It was primarily developed by Christian Huygens. And next, the quantum theory of light. It suggests that the light is made up of tiny packets of energy called photons. These photons have both particle and wave properties, explaining phenomena like the photoelectric effect. This theory was developed by Albert Einstein and forms the basis of quantum mechanics. But in this lesson, we are going to study the reflection and refraction of light. For this, we consider the notion that light rays travel in straight line. What is reflection of light? When a light ray strikes a smooth polished surface like mirror, it bounces back. It is called as reflection of light. We can study the reflection of light with the help of mirrors. Mirror is an opaque object with shiny reflective surface. It is because of the reflection of light we will be able to see our images in mirrors. What is refraction of light? When a light ray passes from one medium to another medium, its traveling speed changes and results in change of its direction. This phenomenon is called refraction of light. A straw in a glass appears to be bent. This is due to refraction of light. We can study the refraction of light with the help of lens. Lens is a transparent object usually made of glass. Eyeglasses are the examples of lenses which use in our day-to-day life. First, let us study the reflection of light with the help of mirrors. This is a plane mirror. When a light ray strikes a plane mirror, it gets reflected back. According to the laws of reflection, the angle of reflection is equal to the angle of incidence. Image formation. Plane mirrors create virtual images that appear to be located behind the mirror at the same distance as the object in front of the mirror. These virtual images are not real. That means they cannot be projected onto a screen. They are formed by the apparent intersection of reflected light rays when extended backward. Size and magnification. The size of the image in a plane mirror is the same as the size of the object. There is no magnification, means that objects in a plane mirror appears to be the same size as they are in reality. Laterally reversed. The images formed by plane mirrors are laterally reversed, also known as left-right reversed. This means that if you raise your right hand in front of a plane mirror, your image will appear to raise its left hand. Now, let us understand the reflection of light by spherical mirrors. A spherical mirror is a curved mirror and it forms the pot of a sphere. Spherical mirrors are of two types. 1. Convex mirrors and 2. Concave mirrors. A convex mirror is a type of a spherical mirror that has an outward curved reflective surface. A concave mirror is a type of a spherical mirror that has an inward curved reflective surface. To understand reflection by a spherical mirror, we need to know certain terms. Pole. The center point of the reflecting surface of a spherical mirror is called pole. It lies on the surface of the mirror. Pole is denoted by letter P. Center of curvature. The center of curvature is the center of the imaginary sphere from which the spherical mirror is derived. It lies behind the mirror in case of a convex mirror and lies in front of the reflecting surface of a concave mirror. It is represented by the letter C, radius of curvature. The radius of curvature or of a spherical mirror is the radius of imaginary sphere of which mirror is a part. Principal axis. The line joining pole and center of curvature is called principal axis. We should remember that the principal is normal to the mirror at its pole. That means at the point of pole, the angle between the plane of the mirror and the principal axis is 90 degrees. Principal focus. If a number of light rays parallel to the principal axis are falling on a concave mirror, they all meet or intersect at a point on the principal axis of the mirror. This point is called the principal focus of the concave mirror. In case of a convex mirror, the reflected rays appear to come from a point on the principal axis. This point is called the principal focus of the convex mirror. The principal focus is represented by the letter F. Focal length. The distance between the pole and the principal focus of a spherical mirror is called the focal length, and it is represented by the letter small f. Aperture. The diameter of the reflecting surfaces of the spherical mirror is called its aperture. In this chapter, we are discussing about the spherical mirrors whose aperture is smaller than their radius of curvature. Let us see the relation between the radius of curvature and the focal length. The relationship between the radius of curvature r and the focal length f of a spherical mirror is as follows. For spherical mirrors with small apertures, the radius of curvature is found to be equal to twice the focal length. We write it as r equal to 2f or f equal to r by 2. This means that the principal focus of a spherical mirror lies midway between the pole and the center of curvature. Representation of images formed by spherical mirrors using ray diagrams. Rules for making ray diagrams. Parallel ray rule. For a concave mirror, if a light ray passes parallel to the principal axis, after reflecting, it passes through the focal point F. For a convex mirror, if a light ray passes parallel to the principal axis, after reflecting, it appears to come from the focal point F behind the mirror. Focal ray rule. For a concave mirror, if a light ray passes through principal focus, after reflection, it emerges parallel to the principal axis. For a convex mirror, if a light ray is directed towards the principal focus, after reflection, it emerges parallel to the principal axis. Center of curvature ray rule. For a concave mirror, if a light ray goes from the object to the center of curvature, after reflection, it retraces its path back to the center of curvature. For a convex mirror, if a light ray is directed in the direction of center of curvature, after reflection, it retraces its path. The position of the image will be at the focus F. The size of the image is highly diminished and point-sized. The nature of the image is real and inverted. Case 2. If the position of the object is beyond C, the position of the image will be between F and C. The size of the image is diminished. The nature of the image is real and inverted. Case 3. If the position of the object at C, the position of the image will be at C. The size of the image will be same as object. The nature of the image is real and inverted. Case 4. If the position of the object is between C and F, the position of the image will be at beyond C. The size of the image will be enlarged. The nature of the image is real and inverted. Case 5. If the position of the object is at F, the position of the image will be at infinity. The size of the image will be highly enlarged and the nature of image is real and inverted. Case 6. If the position of the object is between P and F, the position of the image will be behind the mirror. The size of the image will be enlarged and the nature of image is virtual and direct. Uses of concave mirrors. Concave mirrors are used as shaving mirrors, dentist mirrors. They are also used in the reflectors of torchlights and vehicle lights.